Hi guys, we were discussing about motion of a charged particle in a magnetic field. So a charged particle shows a peculiar behavior when it is in uniform magnetic field. Suppose if you can leave a charged particle in a uniform magnetic field, so it is deflecting, it changes its direction due to because a force which acts on the particle. Now that force is due to because of the velocity of the charged particle and the magnetic field direction. Yet they both are vectors, so the resultant will act on the charged particle that causes the deflection in the charged particle. This we can understand by applying the Fleming's rule. If theta is the angle between the velocity and the magnetic field and the component of velocity which acts on the magnetic field. Now if you can use Fleming's, if a positive charge, if you can use left hand rule, now the resultant force direction will be perpendicular. Now this force magnitude we represent as F equal to Q times V bar cross B bar, and the direction we can represent with the help of the Fleming's rule. Now what happens if we can take for electron, which is another charge, opposite charge. So we can use the same electron, but this time the force will act in the downward direction, which is opposite. Now here I would like to discuss some particular cases. Since the formula contains F equal to Q times V bar cross B bar, in vectorially we can write that F equal to Q times VB sine theta. So here theta is angle between velocity and magnetic field. So what happens for different angles? What happens if theta equal to 0 degree and theta equal to maybe 90 degree or theta equal to at any angle? So let us try to visualize that. So what happens first if theta equal to 0 degree? If theta equal to 0, it means velocity equal to 0. So that's the reason. If there is no velocity, there is no force. So this is the case of a stationary charge. Now if velocity equal to 0, as the first case we can take, means there is no force which is acts on the charge. Correction, that's not the theta equal to 0. For the first case, if we take that, if there is no velocity, if charge is at rest, charge is at rest in magnetic field. If charge is at rest in magnetic field, the velocity component equal to 0, so the charge do not experience any force. Now let me take the second case. In the second case, what happens if the theta, even though charge is moving, but charge is moving parallel to the magnetic field. In the second case, if charge is moving either parallel, maybe same direction to the magnetic field or opposite direction to the magnetic field. Now here you can take the theta. So theta value equal to 0 in the formula. F equal to Q VB sine theta. So theta equal to 0. Sine 0 value goes to 0. The force on charged particle equal to 0. Means the charged particle do not experience any force. So it moves in the same direction and it is moving, because there is no resultant force which affects. Same thing happens if it moves in opposite direction, because sin 180 value also equal to 0. So if charge moves in parallel to the magnetic field or in anti-parallel to the magnetic field, it won't experience any force. But what happens if charge moves perpendicular to the magnetic field? Yeah, this is the different case what we need to study. What happens if theta equal to 90 degree? Means if charge is moving perpendicular to magnetic field. If charge is moving perpendicular to magnetic field, so if you can substitute that value at here, F equal to QVB sin 90 degree. Sin 90 degree value equal to 1. I will get the resultant force F equal to QVB. The force which is experienced on the charged particle equal to QVB. And this force makes the charge move in a circular path. So if a charge is moving in a circular path, so it means there should be two forces should act. What are the two forces there? One is the magnetic force. So one is magnetic force, and second one is, so here what I got, this is magnetic force. And if any object in a circular motion, that another force automatically comes into picture, that is due to centripetal force. So this situation comes when the charged particle enters in magnetic field at an angle of 90 degree. If a charged particle enters in magnetic field, so here you can take the diagram, the magnetic field is shown as a cross, so it means the magnetic field is going inside the screen, and the angle between B bar and V bar, velocity of the charged particle, equal to 90 degree. Now the force F equal to QVB sin theta, here theta equal to 90 degree, so F equal to QVB sin 90 degree. So sin 90 degree value equal to 1. Now the force, the magnetic force, F equal to QVB. So this is magnetic force. Now this force causes to move the particle in a circular path. So that's where the charged particle moves in circular path. Either charged particle, either electron or positron, any charged particle you take, it moves in circular path. So when any object moves in circular path, so that object will experience a centripetal force. Now the centripetal force, the formula mv square by r equal to magnetic force. A magnetic force equal to QVB. Now from this expression, if I cut like terms, mv square by r equal to QVB, here the velocity is common factor on both sides. Now try to get the expression for r equal to mv upon QB. So this is the expression for radius of the circle. So the radius of circle is purely depend upon mass of the particle and velocity and charge and the strength of the magnetic field. And here you can see the radius is inversely proportional to the strength of the magnetic field and inversely proportional to the magnitude of the charge. Okay. Now if it is radius, can we get the time period of revolution? Period of revolution in circular motion. So how can we calculate? Period means I need to get time. So we know the velocity formula, velocity equal to distance upon time. So distance in circular motion is a 2 pi r, total circumference, and time we can get as t and equal to velocity. So the period of revolution t equal to, if you can exchange this one, the period of revolution t equal to 2 pi r, the circumference of circle upon velocity v. Now we already know the value of radius. Try to substitute that. Time period t equal to 2 pi upon radius value, here we got it, how much it is, mv upon qb upon velocity v. Now velocity term gets cancelled, both numerator and denominator. Now which is the leftover, the period of revolution t equal to is 2 pi m upon qb, the time period of revolution. Now here also the time period of revolution is inversely proportional to magnitude of charge. Why I am stressing the magnitude of charge? Because if later if you can compare, if you release in magnetic field an electron, proton, deuteron, neutron, like that, because these all having the different magnitude of charge. Now which will move fast and which will move slow and which is move in longer circle. So to compare that, so this kind of interpretation is very helpful. So period of revolution for a moving charge in a uniform magnetic field t equal to, it's 2 pi m upon q by v. But it is handy to express period of revolution in terms of frequency. Therefore the frequency of revolution, what is the relation between frequency and time period? Frequency f equal to 1 by time period. So I can get frequency of revolution f equal to 1 by time period. Therefore f equal to time period value, here we already got 2 pi m upon qb. Now if you can rewrite this expression, f equal to frequency equal to qb upon 2 pi m. If you remember frequency, number of revolutions per second. Now the frequency of revolutions. Now frequency is independent. Here you do not see any velocity term and radius. So this frequency is purely depends upon the mass of charged particle and magnitude of magnetic field or strength of the magnetic field and the charge, the magnitude of the charge. So this frequency in later terms we call as cyclotron frequency. Here I can tell about cyclotron. Cyclotron is a device which is useful to move charged particle in a magnetic field. It's an experimental device. So by good luck that concept is deleted for the present syllabus. So I am not going to talk anything about that. But the frequency of a revolving charged particle f equal to qb upon 2 pi m. So here I got so many expressions by making equal if any particle moving in a magnetic field. So we need to remember that the centripetal force which is acting, that is causes to balance the magnetic force, because since it is moving in a circle, so the object which is moving in a circle, so obviously this already comes into the action, the centripetal force which always equal in this case the magnetic force. So from here we went ahead to find the radius of the circle. Now the radius of circle is purely depend upon mass of the charged particle and velocity, and it is inversely proportional to charge of the particle and strength of the magnetic field. And after we express time period of revolution. So period of revolution t equal to 2 pi m upon qb, and the same period of revolution we express in terms of frequency. So the frequency, number of revolutions in given second, is known as frequency. The frequency equal to qb upon 2 pi m. Let's try to visualize how the magnitude of charge affects the radius of the circle. So the charge particle here moves in a circular path. So the circle having a radius, the expression for radius equal to mv upon qb. Suppose if we can release three different charged particles, one is proton of mass m, charge q, and neutron, its mass 2m and charge same q, and alpha particle which is having mass 4 times but charge here it is 2q. Now here try to understand the radius of circle, because the radius of circle is depends upon mass and charge. So that's the reason the different particles are moving into the different radius, different circles. Other than that, if you can check that the same with the electron and proton. Electron mass and proton mass slightly difference is there, but they both are having same charge. That causes they both obviously makes the same circle of radius. Now this is the case happens when the particle moves perpendicular. The velocity of particle is perpendicular to the magnetic field. Now let us understand an interesting case. What happens if the particle moves at any angle other than the 0 degree, other than the 90 degree? Suppose if the particle is entering in the magnetic field at any angle. So this is very special case. So this case goes at any angle. Some random, some arbitrary angle. Now velocity is a vector, so that vector is resolved into components. So that horizontal component and vertical component. A theta is the angle between the velocity vector and the magnetic field direction. So you can clearly visualize at here. If the charged particle, positive charged particle, velocity is resolved into two components. Now the horizontal component and vertical component, they too play a very important role to get a different type of motion. Now here we can see the charged particle is not moving in a circle, it is moving in a helical path. So here we need to understand what could be the reason for the charged particle moving in a helical path. So maybe it is the cause of the velocity component, and which of the velocity component, either horizontal or the vertical component. So I want to play it back. You observe that very carefully. If the charged particle is entering in a magnetic field at any angle, so the velocity is resolved into its components, its horizontal component and vertical component. Because of the component interaction with the magnetic field, that causes the positive charged particle motion in an helical path. So let us try to understand what could be the cause and what can we get mathematical help to understand the helical path motion. if a charged particle moving with a velocity not in the same direction of magnetic field or not in the perpendicular direction of magnetic field, then the velocity component perpendicular to the magnetic field creates a circular motion. And suppose if the component of velocity parallel to the field moves the particle into the straight line. So this is what happens here if a particle moves at an angle. The velocity having two components, one is perpendicular component and one is parallel component. Now in these two components, the component of the velocity parallel to the field that moves particle in a straight line, and the component of the velocity perpendicular magnetic field creates the circular motion. So this component of velocity creates circular motion, and this component, parallel component, creates the particle moves in a straight line. Then only we can get helical path. So the particle has to move circle, then after it has to move forward. So here the two components, they play a different role. So let us try to understand that. Since we have the radius formula here itself, the radius r equal to mv upon by qb. So that's what we calculate, the radius of a particle which is moving in a circle. Now here velocity perpendicular component. So here we can see, be careful, where is the theta? Now here the theta is making an angle at here with the x-axis. The perpendicular component is along that direction. Here we can take that perpendicular component is equal to v sine theta. So here the perpendicular component equal to v sine theta. Now to find the radius, because the perpendicular component is the responsible for the circular motion, so in this radius we can substitute that. So r equal to m times v perpendicular upon qb. So if you can put that value at here, so that will changes to mv sine theta upon qb. Now here I notice an interesting change. Now the radius is not only depend upon mass of charged particle and velocity of the charged particle, and it depends upon now theta. Now if theta value changes from 0 to 90 degree, it means the circle radius also gets changes. So that's where the sine value changes more. From 0 to 90 it goes to maximum. So in this special case, the radius of the helical path r equal to mv sine theta upon qb. Anyway, we got the radius. Let us substitute in the time period. So in the earlier expression we got the time period t equal to 2 pi r upon v, circumference upon velocity. So here the velocity equal to perpendicular component. So this, if we can rewrite, that equal to 2 pi upon perpendicular component velocity equal to v sine theta times r. Here the r value right above you have mv sine theta upon qb. Now if we can cut the like terms, the qb, v sine theta and v sine theta gets cancelled. The period of revolution, time period equal to, here I can get 2 pi m upon qb. So in these two cases, when the particle is moving in an angle, the time period 2 pi m times qb. If you can notice, this time period in this case at any angle and the time period in the previous case at an angle of 90 degree. They both have the same. So if you can keep these two parallel, you can see these two expressions which I derived earlier and which I derived right now. So this is at an angle of 90 degree. So there is no change at all. It means the time period of the revolutions in this case, it won't change, but the velocity gets changes. That is due to because of the perpendicular component. I hope you got the difference. Not only that, the radius also gets changes. Now here we need to define one more very important thing, that is known as pitch. So pitch is in regular way I can define as per we know that velocity equal to distance upon time. Yeah. Now what can I write? Distance equal to velocity into time. Suppose in this special case I am having velocity two component, horizontal component, vertical component. Yeah, parallel component and perpendicular component. Perpendicular component is responsible for the circular motion, but the parallel component, suppose if I multiply velocity parallel component with the time, and this we call at about distance, but distance in this particular I can show at here, this is called the distance between two circles I can, or two rings, any word you can give. But that distance have a particular word which is known as pitch. If you can make that pitch just like one and another just like that. So if you can calculate the pitch means the distance between these two. So this we call as pitch. It's pitch. Okay. How can you get that pitch value? Pitch equal to the product of perpendicular components multiply with the t. Here the t is nothing but period of revolution, capital T. Keep it in mind. Now, so that is my next to get it. Pitch equal to the parallel component of velocity times the period of revolution is equal to t. So here I can get the parallel component here equal to v cos theta times period of revolution here equal to 2 pi m upon qb. Now we end up with the pitch equal to 2 pi m v cos theta upon qb. So this is the expression for pitch. Now in this special case we got it two different things, that is, since the velocity of the charged particle in uniform magnetic field makes at any angle, so that causes the resolution of the velocity components, that is perpendicular components and parallel components. The parallel component equal to it's cos theta, and v sin theta is responsible to make the charged particle in circular motion, and v parallel component, since it's a helical, after making circle it move ahead. It means it is the responsible for to move the charged particle move ahead, or otherwise here we can call that as a length or horizontal distance. Now the pitch is the horizontal distance between two circles, two consecutive circles. The pitch is the horizontal distance between two consecutive circles. Who is responsible for the pitch? The parallel component of velocity vector. Okay, let's visualize that. So these kind of lighting effects you might be observed. So this is the natural phenomena, and these lightnings always occurs at the poles 24/7. What could be the cause? The starting point is at here on the surface of sun. We know that sun is a source of energy. So there nuclear fission fusion reactions takes place. At high temperatures, all these helium gases and all, so they already in the state of melt. And we already learned that a charged particle is a source of magnetic field. It's a powerful statement, as I said. A charged particle is a source of magnetic field. Now these all charged particles, when they combine or when they fuse, a huge magnetic field is already present on the surface of sun. So sometimes what happens when certain solar storms happens, every time it happens 24/7, at every moment solar storms are happening on the surface of sun. So this is a solar storm. Usually in our storm, when it happens on earth, it carries water from the sea. But in the solar storm happens, it carries certain mass of the sun. But that mass is in the gaseous state, which that is known as plasma. A huge mass, huge means huge, a huge mass which is carried out, which is pushed out just like a stretched rubber band. Now at here, this huge mass gets separated from the sun. So when it gets separated from the sun, so it travels all over the universe. Now at here it detaches, the rubber band stretches and it will be detaches. Now the huge mass is carried and it is traveled all the way from the sun to the earth atmosphere. Yeah, this is a very close picture of the solar storms. So those are the very powerful. So when they travel all over the universe, all the way from the sun to our galaxy, so when it reaches to our earth atmosphere, when it passes to the one after another planet, and since it reaches finally to our environment, so when it reaches to our environment, our earth is having atmosphere, and before that the earth having its own magnetic field. Yeah, that's the exact cause. The earth having its own magnetic field, it's very powerful own magnetic field, that we already know that. So this is the pattern of the earth natural magnetic field that we will study in the next concepts. It's just like a bar magnet. Or if you remember, this is also same pattern of a current carrying solenoid, because current carrying solenoid is equivalent to a bar magnet. Now here two magnetic fields are seen. So this is the earth magnetic field and this is the storm which is carried from the sun. And this plasma storms contains a charged particles. The charged particles are, they are the responsible. Now here the interaction, the solar flares are interacting with the earth magnetic field. So our earth magnetic field is giving a protection shield from that sun plasma. So that protection shield is interaction of the sun plasma with the earth magnetic field. So that's the reason for the formation of the aurora borealis. So these lightnings only we can see at the poles 24/7. There is no day and there is no night. So the spectacular lighting affects the charged particle here. Here the charged particle motion, they move in the earth atmosphere in a helical path because the interaction of the magnetic field. So this is due to the interaction of the charged particle with the magnetic field. The charged particles, the perpendicular component is causes to move in a circular path, but the parallel component, the velocity parallel component, it causes a helical path along with that, supposed to draw properly. Yeah, just once you Google it, or you can refer your textbook to get the further knowledge. So this is also known as northern lights, or this is called aurora borealis. If you have more interest, try to get what could be the reason for different colors. So sometimes mostly we can see green, yellow or violet or different colors. So what could be the cause for the different colors at here? So think common sensely, our atmosphere having different kind of gases, and they all are the responsible for these spectacular colors. Just like in the firecracks, different elements are responsible for the different colors. Here also something like that. Try to get it. Yeah, this is all about for today's concept. I thought to say one more point at here. That is a simple point. Suppose if a charged particle, a positive charge, because this is a simple concept, I cannot add it anywhere. If it is a charged particle of charge plus q, by default it's having its own electric field. What is electric field? You can write electric field equal to force per unit charge. Now what the force expression? Force due to electric field, I can write that electric field times charge, EQ. Now right now we learned that a charged particle also experience a magnetic field. So that magnetic field, what we got it, F equal to Q times V bar cross B bar. Okay, so this is the force due to magnetic field. Now if a charged particle is moving in a magnetic field, a charged particle is moving in a magnetic field, so by default it is already having its own electric field, and now because of the presence of the magnetic field, it got another force, that is the force due to magnetic field. So here whenever you write the force expression, okay, if you are writing force expression separately in the electric field and magnetic field is okay, but you keep in mind when a charged particle is moving in magnetic field, it's already having its own electric field. Now if we can express total force, the force total on a charged particle due to the force due to the electric field plus, sorry, here it is plus, and the force due to magnetic field. Yeah, here two forces are already existing if it is moving in a magnetic field. Now if you combine these two forces, the force F equal to Q is common factor, I can pull the Q out, and E bar cross, sorry, it's a plus, E bar plus V bar cross B bar. And this force, the total force, having a name which is known as Lorentz force. L-O-R-E-N-T-Z. It's a Lorentz force. The force which is acting on a charged particle due to because of the both electric force and magnetic force. So here I am giving a reminder, you should not forget, if a charged particle is moving or a particle having charge, By default, it's having its own electric field. Now the total expression, the Lorentz force F equal to Q times E bar plus V bar cross B bar. Okay, here whenever we talk the moving charge in the magnetic field, so we will neglect that electric field effect on the charge, because on the charge its own electric field should not affect. Its own electric field do not affect on its own. That is a default. Just like suppose you are spraying a perfume on by yourself, the smell you will get of that is very less. So this is the same reason the charge do not experience more electric field of its own, but it will experience electric field of some others, but it do not experience more or negligible, or you can take that up to ground, up to zero. It do not affect its own electric field. This is all about a charge moves in a motion of a charger particle in a uniform magnetic field. A lot more I discussed it here. At the end, hurriedly I discussed about that Lorentz force. Okay, so keep the things clear and try to apply and practice those all the radius of and pitch formula and radius and of in the circular motion, especially when it moves in an angle of 90 degree, that causes a circular motion, and when makes at any angle. So this is one of the very important concept at this current chapter in the examination point of view.